If I tell you that the derivative of some function dy dx is equal to the cosine of x, and ask you to find y, you can say, well, what has a derivative that's cosine x? I guess sine x, and I could add any constant in there and its derivative would be 0. So here are a bunch of functions whose derivative is cosine x, but our big question is, are these the only ones? So are there more besides just sine x shifted up or down? Is there some other function yet to be discovered, or that I haven't considered, that might actually have that same derivative? And the answer is no. Okay, now in order to see that that answer is correct, it's going to take a couple new theorems and a couple corollaries to those theorems in order to do that. So we're going to introduce two theorems that we haven't seen before. One of them is called Rolle's theorem, and then we'll have the mean value theorem, and then we'll have two corollaries. So from the mean value theorem we'll get corollary 1. A corollary is another word for a theorem, but it's correlated to or comes along with some other theorem. So we'll have this corollary 1, which just comes quickly from the mean value theorem. And then there's another theorem called corollary 2, and that comes quickly from corollary 1. So, okay, in fact, really the mean value theorem comes quickly from Rolle's theorem, but the mean value theorem is important in its own right. That's why it gets a special name. All right, now, before we do that, I need to remind you of a couple things that we already know. The first thing we already know is the extreme value theorem. It was not something that we could prove, but it said that if you had a function that was continuous on a closed, I should add a word here. It should be continuous on a closed bounded interval a, b. Then that function has an absolute max and an absolute min. So, and where could that absolute max and min occur? Well, either on the boundary or at a place in the interior where the derivative was 0. So if the derivative exists, right, then the derivative would have to be 0 there. We used that before when we were maximizing and minimizing functions on a closed bounded interval. We just found places where the derivative was either 0 or undefined, and then we checked those places and the endpoints in order to find the max or min. Those two ideas are important for Rolle's theorem. So Rolle's theorem says, suppose you have this function and it's continuous throughout some closed bounded interval and it's differentiable at every point in the interior. So if this function has the same value at the left endpoint as it has at the right endpoint, so if g of a equals g of b, then there's at least one place in between a and b where the derivative is 0. Now geometrically this is pretty simple. So we have 2 points, right, a and b, and when you plug in a, or if you plug in b, the same value comes out. So g of a equals g of b. If your function is continuous and differentiable, no matter how you try to draw it, you come up with at least one place. I can see here there are like 3 places. At least one place where the derivative is 0. So that's what they're calling C. Now, so it seems kind of geometrically clear that that should be true, that Rolle's theorem would be true. Even if I tried to draw maybe another function, let me use a different color here, so some other function that was continuous and differentiable, there would still have to be some place in between a and b where the derivative went to 0. You might even try to cheat by drawing maybe a straight line, but then the derivative is 0 the whole time, right, for every place. So Rolle's theorem just says there's at least one number in between a and b where the derivative is equal to 0. Now, in order to understand, we can see why it's true. It's kind of obvious from a picture, but a picture doesn't really cut it because I can't draw all possible continuous differentiable functions between those 2 points. So a picture may not be so convincing, but we can give a pretty convincing argument for Rolle's theorem, so we could actually prove this. So if we what we should notice first is g of x is continuous on a closed bounded interval, and that means the extreme value theorem applies, right? If the extreme value theorem applies, then g has to have a max or a min, right? Has an absolute max. It has an absolute max and an absolute min on a b, and either that absolute max and absolute min both occur on the endpoints, or one of them, at least one of them, occurs in the interior. Let's suppose that the max and min both occur at the endpoints. If the max and min both occur at the endpoints at a and b, then since g of a and g of b are equal, the max and min are the same value, which means that there can't be any value lower or higher, so the function's completely flat, right? In that case, every point between a and b has a zero derivative. If not, though, then either the max or the min, or possibly both, occur in the interior. And we saw in that theorem 2, right, that if there's going to be a max or min and the derivative is defined, which we're assuming, then the derivative has to be 0 at that max or min. So then there's some point in the interior where the derivative is 0. So that's kind of a sketch of why Rolle's theorem has to be true. It just comes from the extreme value theorem and this first derivative theorem for derivatives. Okay, so there's Rolle's theorem. It's useful in its own right, but it's particularly useful for proving the mean value theorem. So the mean value theorem says, suppose you have a function that's continuous on some closed interval and it's differentiable on the interior of that interval. So that's just like what we were assuming for Rolle's theorem, but in the mean value theorem we don't make any assumption about the value of the function at the endpoints. So then it says that there's some point between a and b where the instantaneous rate of change of f matches the slope of the secant. And that's clear if we draw a picture. So if we have our function is continuous on this interval from a to b, then if you plug in a, you'll get out some value f of a, so there's some point in the ground. And you plug in b, you'll get out some possibly different value, f of b. And what this is saying is that if the function is continuous and differentiable, then if you calculate the slope of the segment joining these, right, that would be f of b minus f of a over b minus a. There's some point in the interior, at least one point, where the slope of the instantaneous slope matches the slope of the secant. In this case, we can see there are actually probably several, the way I've drawn it. But what the mean value theorem says is it's impossible for the function to be continuous and continuous on the closed interval and differentiable on its interior without having at least one point where the slope matches. Let's see, here's one. Tried to be as non-wiggly as possible, but I still ended up with some point here where the slope, the instantaneous rate of change matched the average rate of change, or the slope of the tangent matched the slope of the secant there. Okay, we can kind of see why it's true from a picture. How would you actually prove it? And the way to prove it is to use Rolle's theorem. Make a new function from your function f. Here's how to do it. Take this constant f of b minus f of a over b minus a and multiply it by x minus a, then subtract that from f of x. This new function g has a cool property. If you plug in a, you'll get out f of a minus f of b minus f of a all over b minus a times a minus a. But a minus a is 0, so that's 0, and so it wipes all that out. And so all you get is f of a. So our function g has the same value as f at a. But then if you plug in b, you get f of b minus f of b minus f of a all over b minus a times b minus a. So the b minus a's cancel, and you have f of b minus f of b minus f of a. If you distribute, you get a negative f of b and a positive f of a, and that negative f of b wipes out that one, so you get f of a again. So this new function g is continuous because f is continuous, and this is just some line. That's definitely continuous, and the difference of two continuous functions is continuous. So this function g is continuous, and it has the same, and it's differentiable. In fact, what would its derivative be? Well, the derivative of the difference is the difference of the derivative, so we get f prime of x minus f of b minus f of a all over b minus a. The derivative of x minus a is just 1, so times 1. So g is definitely differentiable on the interior because f is, and this is its derivative. So g actually satisfies Rolle's theorem, which means there's a point c between a and b where g prime of c equals 0. But on the other hand, g prime of c would be f prime of c minus f of b minus f of a all over b minus a. And that basically gives you what you wanted, right? That there's a point between b and a where the derivative of f is equal to f of b minus f of a all over b minus a. So that's how the proof of the mean value theorem goes. It will follow directly from Rolle's theorem.